changes that affecting optimality here, what changes are affecting the feasibility, or what changes affecting optimality and feasibility. Yeah, depend on, is it changing in the coefficient of objective function, is it changing of the using of resources, or additional variable maybe, or RHS or right hand side, which is usually the capacity, for example, or additional constraint, or both, all of them in one. So let's do the analysis sensitivity with the simplex, because we also can do using graphical form, graphical method. Yeah. So in here we have several uh, name here. Optimal solution, the status of the resource that we call shadow price. What is that? We'll discuss. And also what we call a reduced cost. What is it? Yeah, we'll discuss. So let's come to this. Yeah. I will skip this. You can read again. But basically, we go to here. Yeah. This one shows that we have two products. Paint, yeah, chap is paint. This X1 as exterior paint that has to be produced, and X2 is interior paint. Yeah, interior means inside the building, or exterior is for outside the building that need to produce. And the objective function is to maximize the revenue. In this case, profit maybe, yeah. Okay, revenue. Which is Z, maximize Z, and based on this, you can read it again later, but it's 3x1 plus 2x2 because of the price. The revenue of x1 is 3,000, and the revenue of x2 is 2,000. And in 1,000, we have 3 and 2, okay, for the objective function. And for the constraint, batasan is constraint related to bahan baku or raw material, and related to requirement of daily requirement, you can say, and non-negativity, of course. So based on this problem, we have this x1 plus 2x2 less than 6, which is because of the availability of raw material A. Yeah. And then for this 8 ton, 2x1 plus x2 less than 8 is because of the availability of raw material B. Yeah, so this is about raw material. And then here is additional requirement that for the demand of interior paint, or the X1, will not be more than 1 ton extra from the X2, meaning interior is X2. So X2 will not more than 1 plus X1, or X2 minus X1 less than 1. Yeah, it's based on the story, you can say. I'm just make it faster, yeah. And also the maximum demand of interior paint, which is X2, is 2 ton. Yeah, daily demand is 2 ton, so that's why X2 will not be more than 2. This is just a requirement, yeah, or based on what the company want to limit themselves. Yeah, of course with no negativity. So based on this, if we do the simplex, we put in the standard form like usual. Everything in here is just a primal simplex, yeah. Normal, the very first simplex that we learned. S1, S2, S3, S4. Okay. And then here. And before when we the next page is to find out what's the optimal solution after 1, 2, 3 iteration. Yeah. It's we can see, okay, normal simplex is you can have it like this. Yeah. But then we have this, what's the meaning of S1, S2, S3, and so on? Previously, I was saying that it's just artificial variable, we can say, yeah. Additional to make between the left side and right hand side equal. But if we now going to the sensitivity analysis, then there is a meaning of S1, S2, and S3. Yeah, S1 actually, because of the first constraint, is related to the availability of raw material. That means S1 is actually what's left of raw material A. S2 is also related to the raw material B. That means S2 is what's left of raw material B. You can see here, this is 6 is the raw material A. So whatever you produce is cannot be more than 6. If you produce X1 and X2, whatever it is, how many it is, I mean, yeah, use the raw material A5 for them, then S1 must be 1. So you have 1 ton left out of 6 because you use only 5. If it's 0, that means you don't have anything left. Yeah, that's what it means. Also, S2 is related to raw material B. Yeah, here. Okay, and the other one is based on what's the leftover, based on the requirement from the daily. Yeah, here. So everything has meaning now, depend on what's the story. Okay, and here we mean which means what's left or from the x2 minus x1, s3, and s4 is what's left of the maximum of x of demand of X2, because the maximum demand is 2 ton. If the demand is maximum is 2, but you only produce 1, what's left is S4, mean only 1. You only deliver 1 ton out of 2 tons, for example. That means what's left is 1 ton. Yeah, related to the maximum. Okay. All right. This is the simplex. I want you to take a look at this, and sorry, but I need to pause. Just give me 1 minute, okay? Sorry, while you look at it. From this final result, there you go. Yeah, we know that x1 we have 10 by 3, which is we need to do you to make 3 and 1/3 ton of x1. I need to make x2 in here is 1/3 ton of x2, or the product x2. And the z is 12 to third, or meaning $12,667. Yeah. And we can see in here from x2, x1, s2 to s4, there is no s1 and s2, which mean the s1 and s2 is 0. If there is no S1, S2 in here, that means S1 and S2 is 0. And what it means by S1 and S2 0, there is no more left. All of the raw material A and all of the raw material B is 0 now. That means we all finish up the raw material, and that's why we stop, because we cannot produce more. Yeah, which mean actually good, right? You use all to gain revenue. Yeah, which is good. Okay, but this is the thing: if you show this result to say the manager or the client, then well, this is good. Okay, everything is used for, and we got 12,000 ish, 12.6 thousand dollar. Good. Then the manager might think, okay, this has been used all. What if I can add something? Yeah. What if I can add the capacity of A was 6 and capacity of B was how much? 8. What if I add the capacity? What if I add the right hand side in here, not 6, not 8. I might gain more profit, more revenue, right? So this is then start from this point, the questions start to be asked to you as the one who make this analysis. What if? Yeah. So here, what if I add more? Because we know that S1 and S2 is 0, so there is no more left. What if I add more? Okay. So what will be affected? How much revenue can be increased by adding? Actually, from this simplex table, we can actually already see how much increase of the z if we add more. Yeah, here. Look at this coefficient. From the optimal table, look at this coefficient. This will tell you how much will z change based on adding raw material A. S1 is related to raw material A. S2 is related to raw material B. How much will increase? So if we add 1 ton of raw material A, the dollar, the Z, will increase as 1/3 thousand. Isn't this is thousand? If we add 1 ton of the capacity of raw material B, then it will be used also, and it will increase the revenue by 4/3, yeah, thousand. So this can get you quickly, yeah. You don't need to rerun the program, you can say. This is manual, but if you do it by computer, maybe it's faster, but if it's something that is more complex, then it might need time. And if you know about this knowledge, yeah, then you can quickly tell how much will it increase, yeah, for every ton, for every unit of raw material A and unit of raw material B. Okay, here. Okay, well, this is what we can see. Thing to be muted again. There you go. Okay. Now, there is another now, what is called reduced cost. Only work for variable that is 0, and for the previous case, there is no information about this. What is reduced cost? So this is similar base problem, but different coefficient. Yeah. Basically, on the final, we have this result. Yeah. For example, this is a similar case. This is the final result. For example, you see here S1, X1, S3, and S4. There is no X2, which mean actually the optimality is not to produce X2 at all and only produce X1. Yeah. So, okay, this is for example. So X2 is not producing at all. Yeah. So we can see that X2 related it's here. The coefficient is 2 in the yellow one. So this is also important information as what we call a reduced cost. What is it? It means that if we force to produce X2, say your manager asks you why we don't produce X2, we have X1, X2, why we only produce X1? Yeah, and we have the raw material for X2, and then it's just ready, but why we don't produce? If he or she asks you what the effect, if you still forcing to produce X2, then every 1 ton X2 product, you will lose $2,000. In this case, two if it's in thousand. So if this is the optimal solution, that means if you produce this, forcefully produce this, you will lose, not add, but lose $2,000. every ton. So this is what it means. That's why it's cost, reduced cost, even though it's not just cost, just reduced. Yeah, if it's profit, I mean reduced profit. But anyway, that's just a name, a standard name for it. Okay, it means you actually reducing what you're supposed to be optimal. You're gonna getting away from the optimal. Yeah, if you forcefully make the one that is not mentioned in here. X2 is not mentioned in here, meaning it's zero. You should not produce X2. Otherwise, if you keep losing, if you producing, you lose $2,000. Okay, that's reduced cost. Yeah. So let's continue with this. Like, okay, now if we add, we can get more money, we can get more revenue. But how much should we add? Can we add like a lot? Say if we get, say, remember the previous case, if we get 1 ton of raw material A, we'll have one third $1,000, yeah. Yeah, but if that's if we add 1 ton, is it fine if we add say 10 tons? 15 tons. Is it still okay? Now, this is to check. Yeah. There is a limitation to change. Yeah. The availability of A. Okay. And also the B one as well. Because if it is outside the range, then it's going to have a different effect. Okay. Now, in here, it's about A. Raw material A can be added or reduced. Yeah. So D1 will be positive if we add more raw material A. D1 will be negative if we decrease or reduce, I mean, raw material A. Also for B, we put it as D2. So previously it was S1 and S2. Now is just make it D1, D2. Yeah. Positive if it's we add more of raw material B, and negative if it's we reduce the raw material B. Okay. So now we have D. Going back to this, yeah. Going to this. You don't need to see the top. This is the one that I usually not do, but just go straight to the bottom box. Yeah. Bottom box. So here we already know this coefficient, which now we are talking about raw material A. So we see what's the coefficient under S1, which relate to raw material A. Okay. Here. We can see the coefficient here. Yeah, let me check one more time. Now, this is the optimal solution, yeah, just like this one, okay? But now, we want to know what's the effect on the right-hand side, yeah? If we add or deduct D, now, simply use the right-hand side that you have before in here, and plus D1 multiplied with this plus D1 multiplied with this. Sorry, this side plus 1/3 multiplied with D1. 4/3 plus 2/3, 2/3 multiplied with D1. Including this, 10/3 plus minus 1/3 by the multiplied with D1. Sorry, 3 plus 1 minus 1 multiplied with D1, and so on. So this is the way, and this is the formulation, but basically the same, yeah. The new one is the constant, which constant is the old RHS plus the K, which is the coefficient of S1, K is coefficient of S1 multiplied by D, DI, like this, okay? Yeah, and now this is to know the range. You get everything in here, all the right-hand side you can see has to be greater than equal to 0. the minimum value of RHS should be 0 or greater. So everything here should be greater than or equal to 0 or like this. Okay. From here, you can find what is D1 then. From the first one, D1 should be greater than minus 38 and so on. And the last one is D1 should be less than 1. So all of this inequality, you combine it and to find out the range. Yeah, the minimum value of D1 based on this is minus 2. We have minus 38, but it cannot be less than minus 2. So minus 2 is the lowest. And the highest is, we have 10, we have 3, but we have 1. So it cannot be more than 1. Yeah, it cannot be more. So the range is between minus 2 to 1. Yeah, the D. Now, if we put the D back to the RHS, yeah, which is what? 6. Yeah, 6, what is 6? Where is it? Here, this is 6. The maximum capacity of raw material A is 6. Yeah, we want to know the range. If we want to add or reduce, how much can we do it? This is the range. Could be reduced to 4 and could be increased the capacity of raw material A into 7. So we can only increase 1. Yeah, this is the limitation. If you add more than 1 or it become 8, for example, not 6 anymore, 8, because maybe your manager want to have more profit, more revenue, based on this sensitive analysis, then the solution will be invisible. Okay, you will not, it is not possible, you can say. Yeah, you could run it, just change into it and rerun it again. But then you'll have invisible solution. That's what it means. But in this sensitive analysis, hopefully it is faster and without rerun the program, you can quickly say you cannot add more than 1 ton of raw material A, only 1 ton max. Yeah, more than that, we're gonna have trouble. It's gonna be invisible and you're gonna need to find out where is the trouble. Yeah, like that. Okay, including the B. Yeah, including the B, same. Put the original RHS plus the coefficient of raw material B and into D2. Yeah, the minus or plus sign based on the sign of this coefficient and based on this one, the right hand side, the new right hand side. We find out the range and see that D2 can be changed, can be increased 4, or if you want to decrease, minus 2. So the RHS from 8 that it's available, it can be increased into 12 and can be decreased into 6, but no more increasing D to more than 12, or else it's going to be invisible. There is no solution really. Yeah. So this is the range of changing. Yeah. Not just increasing, but decreasing also important. Say, what if we increase this or reduce that? Yeah. Or what if, oh, okay, for next month, we won't have 6 ton of A, we won't have 8 ton of B, raw material B. There is problem with supplier, so maybe next month we only have 6 probably. Is it going to be still fine? Now that question, what if, yeah, the supplier next month they will not be able to send 8 raw material B, only 6. Is it still fine? Now, based on this, you can say, okay, it's still fine. Of course, it's going to be changing the revenue, yeah, but it's still feasible, yeah. What if it's be reduced from 8 to 5? Now, 5 is less than 6. Then you need to give suggestion to your manager that it is not going to be good for us. It's going to be not safe for us. We need to find additional raw material B in this case. We cannot have B less than 6 ton. And for next month, it has to be at least 6 ton. Yeah, it's not going to be good. For example, based on what? Based on this. Yeah, and we find out or push the supplier to still supply the what's left or find other supplier. This is the application of sensitivity analysis in this range. Okay. Then what if both? Then yeah. What is it? Use both. Yeah. Use both. Okay. And then find out what is D1, D2, and then look for yourself. What's the range of this? Okay. That. Okay. Any question from here? Okay. I hope it's clear. Now, let's continue. My time is less than 6 minutes, but I will give you a new link, yeah, Zoom, if we haven't finished. We will not be finished yet, but I will give you a new link, okay? Let's continue. Now, this is a change. What if, again, we change the coefficient of objective function? Now, there you go, yeah. For this example, we use D1, small d1 and small d2, yeah. We'll use this as changing of the coefficient of x1 and changing coefficient of x2, meaning, okay, x1, product x1, if we sell 1 ton, we'll have this money, yeah, revenue, this dollar. What if it changes? Yeah. What if we get less money because of the difficult competition, for example, or the strategy that the company decide to reduce or use part of the revenue for other R&D strategy, for example, R&D plan. Yeah. What if it's changed? Yeah, the revenue is changed for any reason or increase, in fact. Yeah, increase. Yeah, it's what if again. Now let's see. Previously it was capital D, now it's a small d, yeah, for the coefficient of objective function. So we're going back to this example, same paint example, yeah, based on this, yeah. Now we put D now, based on the final, the optimal solution. The D should go in the first line because it's related to the coefficient of objective function. Yeah. So previously it was 1/3 and 4/3. This is 12 2/3. If we want to change the D based on product 1, x1, yeah, what effect on the Z is this? You just need to add the original coefficient plus the coefficient of related x1 multiplied with d1. So it's 1/3 plus minus 1/3 d1. And this one also 4/3 plus 2/3 multiplied with d1. Okay, including the revenue 12 2/3 plus 10/3 multiplied with d1. And thus, for this, for the maximization, all of this should be 0 or greater than 0. Yeah, like this, plus. So all in here should be greater than 0 or 0 or this. Same like that, previously. Yeah. The first coefficient of S1, and then this is coefficient of S2, and this is the right hand side or the revenue. Equal has to be greater than or is equal to 0. From here, we can find out what is D1. Yeah, again, D1 is coefficient related to product 1 or the revenue of product 1. And based on this, we got the range, which is 1 to 4. So if your manager asks, okay, looks like the the revenue of X1 is not going to be 3,000, might be reduced, yeah, uh, into 2,000 because of some strategy of the company to, yeah, use the revenue for other purpose, yeah. So what we will get is only two, for example. What will happen? What the effect on the plan? And then you check in here. Oh, two is still between one and four, so it's still between the range for X1, yeah. That means, okay, we might be sure we can get less revenue, but our optimal solution will not be compromised. We still have the same, uh, we still need to have the same configuration, meaning we still need to produce 10 by 3 ton of X1 and 4 by 3 X2. Yeah. Of course, the Z is going to be reduced, but the optimality or the configuration of how much to produce is still going to be the same. It will not affect the optimality. Yeah, yeah. Including also if we get more money, not 3,000, but say four, still fine, but 5,000, the manager will be so happy, you will be so happy, but then you need to redo it again because the optimal solution will not be the same. It's not going to be this again. It's going to be changed. That's what it means. Yeah, it is. Okay. My time is less than 1 minute, so I will go to the next Zoom link. Yeah, hang on. I will share you the Zoom link. Copy and then chat. I put the chat for the new Zoom link. You can rejoin in that Zoom link. Okay. See you soon. Right. Welcome back. Let me share the screen. Yeah, it's there. Right. Let's continue. Yeah. You can see the news, the sky screen. Yeah. Okay. Let's continue then. Okay. Now, this is for changing the coefficient of X1 or the revenue from producing one product of X1. Yeah. D2, this is for product X2. So we see now, same, we put the coefficient, whatever it is that is not zero, this is zero, so we don't put anything in here. But here, we put the coefficient based on, we add the coefficient multiplied with D2 based on the coefficient related to D2, which is X2. Similar way, yeah, we get all this adjusted on the new coefficient, and all this coefficient need to be greater than or same equal to zero. So we put everything in here, greater than or equal to zero, and we got combine everything and got the range is between 3 by 2 and 6, which means we could reduce X2, the profit or the revenue of X2 from originally, what was originally 2, yeah, 2 into 3 by 2. So we can even less than $1,000. Previously, the revenue was 2,000. Even if we reduce less than 1,000, we still have the same optimality. Yeah. But if we increase, which was usually the manager and the client like, how much can we increase? Yeah. How big from two for the same optimality? We can increase until 6,000. Yeah. to get still the same optimality. If it's more than 6, you need to rerun the program to get the new optimality. Okay, here. And if it's both, still the same. Yeah, still the same. Okay. The same way, and to find out what is D1, D2, and the range. Okay. Okay. So up to this point, any question? If not, then I will continue. Yeah. To the next file. Actually, I also have this graphical sensitivity analysis, but you can try to read it and read it yourself, and then I just want to for us to get still time to discuss about the next um, chapter, which is duality. Yeah. Okay. I'm gonna stop sharing and then share the new one, the new PPT. Okay. Give me some time. There you go. Okay. Okay. You can see now the new one. Yeah, the new file. This is probably the last that might be in the exam, but we don't know yet because haven't I haven't discussed with the other lecturer. Yeah, what's going to be in for the exam, the midterm exam. So here, duality, which is actually part of this, is like introduction to duality, but the complete one you will discuss it with the teacher with the second session. Yeah, which we'll discuss much more. But this is introduction. Still, it might get out in the exam. Yeah. So what is duality? Remember that we have our previous simplex. We call it simplex primal. And then if we have the non and not primal, we use, remember, if we use two phase, we use big M, it's not primal anymore. So why we call it primal? Because we have what we call dual in here. Yeah, we have what we call dual. Okay, and this is why it's called duality concept. Meaning, actually, everything primal will have the dual. Yeah, will have the dual. Here it is the example, yeah, of the dual. So if we have primal like this, the main mathematical formula, maximize z, for example, and there's constraint as are like this, for example, yeah. Remember that b in this case is right-hand side, and this is c is the coefficient of the variable of objective function. Yeah, x is the variable, of course. Yeah, and A is to define what's going on in this constraint. The dual will be like the opposite, but it's not Z. From max Z to minimize W. From CX into BY. Yeah. From AX of the constraint will become AY. And B becomes C. You can see that there is some similarity. The B in here in the dual will raise to the objective function. And the C in the objective function will go down as the right-hand side of the constraint. Yeah. Y is unlimited. Batasi means unlimited. Yeah, here. So, and this is for maximize Ramal. This is minimize Z for Ramal. Again, the dual is kind of like the opposite. Okay. And the reservoir rule, based on the reference, this is in Indonesia, yeah, based on Hillier and Lieberman book and also from Taha book. But basically, you will learn more rules on the second session. Yeah, this is this two to explain this. Okay, what changes? Okay, we go straight to Okay, this is also a table, but sometimes I just don't use it. Yeah, it depends. Just to remember which one is C, which one is A, which one is B. Yeah. And this is changing in the objective function from previously maximize become minimization. Yeah, of the dual, the constraint become this greater than or equal to, and the variable of the constraint in here become unlimited. The y is unlimited, while the x is limited to something, but the y, this is unlimited. Yeah. Okay, so let's go to the example now. Let's go to the example. We have this, the primal example, okay, like this. And if we put in the standard form, we have S now, S1, this one we don't have S, yeah. And then what is the dual? Now, this is what I want to show you. Look down from the panels part, the one that you used to know, standard form. Yeah, this is the coefficient of the objective function, or the variable of the objective function. First constraint, second constraint, and non-negativity constraint. Look, 5, 12, 4, 0. Yeah, the coefficient of the objective function will become the right-hand side of the constraint in the dual. 5, 12, 4, and 0. Okay, first you need to notice. And then the right-hand side of the constraint in the primal will become the coefficient of the objective function. 10, 8 become 10, 8. Yeah. And there is no more x in here, but there is y1, y2. Yeah. What about the left-hand side? What's the constraint going to be? After you put in the standard form, we can check how many columns. This is column related to x1, everything x1 in here, everything related to x2, x3, and s1. Look at the column. 1, 2, 3, 4. There is a 4 column. That means there will be 4 constraints of the dual. 1, 2, 3, 4. Excluding the non-negativity or this or not non-negativity, but describing what is the variable. Yeah. So it's going to be gonna have 4 constraints now. Yeah, because we have 4 columns. What are those 4? You can see again the column. The first, only the constraint you can see 1 and 2. That means 1y1 plus 2y2 less than greater than equal to 5. Greater than equal to this coefficient. Okay. How about the second constraint of the dual? See the second column. 2 and minus 1. 2y1 minus y2 greater than equal to 12. Okay. The third constraint is going to be based on the third column, 1 and 3. 1y1 plus 3y2 greater than 4, including the s. 1s and 0, 0, 0 as well. So 1y plus 0y2 or 0 is greater than 0 also, or y1 is greater than 0. Okay, which means y2 may still be unrestricted, but y1 now is restricted because of this constraint. Okay, very good. This is how you make the dual. Yeah, this maximization is become minimization, and everything, the sign is going to be like this. Until you will go to the second session, then you will learn the changing of this sign. But now we just learn the introduction, the basic. Yeah. Okay. Um, okay. So let's continue with the example now. Yeah. This is primal, and then it's been made a dual. Yeah. We have this based on this primal. Okay. And if we solve each other, we should have the same result. The z is 15 and w is 15. Yeah. If it's not same, that means it's something wrong. Yeah, yeah, for this. So, so what's the purpose of finding the dual? Why not just use the primal? Yeah, here's the thing. Sometimes to find the solution is difficult. Yeah, sometimes depend on the case, depend on the problem. Finding solution of the panel is difficult or too long. Yeah, or stuck. You can say kind of stuck. Yeah, and then the mathematician behind the operational research try to find a way around it. And they found out that, oh, every panel, they have a dual, what we call dual. Yeah. And then when they try to solve the dual, oh, their objective function is actually the same now. Yeah. So the purpose of this dual is when you cannot find too difficult to find, for example, the objective function and the configuration of the primal solution, a primal model, you can try to find a way that to see the dual and try to solve. See, it's probably is more easy to solve the dual. Yeah, you have the same objective function, optimal objective function, which in this case W is 15. For example, you don't know what is Z, but you know W is 15, so there is an optimal solution. Yeah, based on the dual problem. We know that y1 and y2 is not x, but there is an additional analysis that, okay, if the w is 15, y1 is 5, y2 is 0, what is going to be the x? Then there's going to be additional analysis, but basically, if say you cannot find the z, and of course you don't know the x1 and x2, you cannot get stuck. Try to set the dual, find the dual, that means you see that, okay, this problem has a solution. You do not stuck because of the invisibility or any other thing. Yeah. It's just that uh, there is something wrong with the code or something wrong with the settings. Yeah. But there is a solution. W is 15. You have a number. So Z must be 15 too. And then you have Y1, Y2, and then additional analysis we will not discover it now, but maybe later in the session 2. Then you can find out what. So what is, if W is 15, what is X1 and X2? Yeah, okay. That's the main purpose of the dual. Yeah, yeah. Okay, so let's try now. Example, if we actually solve it, this is using the primal. Now we have now the big M for this case because we have equality in here. Yeah, plus R1, put R1 in here, MR1. And this is the way to solve after three iteration. We don't have M in the right hand side. And in here, everything is plus. This is minus 2 by 5, but plus M, so it's actually plus. So this is optimal. And this is the result. The Z is 54, 4 by 5. And X1 is this, X2 here, X3 is 0, and that's what we need to know, right? We want to know what is x1, x2, and x3. We know the result now. Yeah, from here. Okay. This is for the z, for the primal. Say if we want to know now uh, the dual. Okay. Um, what is it? This is a table just to help, but if you need it, sure. If we don't, it's fine. Basically, you want to change from here, standard form, into here. Okay, this is not into here. Yeah, or from this one, the non-standard form, primal into this. Yeah, this table is to help, but the main idea is the same. Yeah, what changes from here? This coefficient in here will become the coefficient of right hand side, yeah, coefficient of the right hand side in here, the primal will become coefficient of the objective function, and also the constraint is same. Okay. um, Now, this should this should not be minus type. I think this is missed type. Oh yeah, this is yeah. Let's check again. But this the yeah, this is using big M, and also there is this unrestricted y1 and y2, meaning y2, sorry, y1 has to be greater than 0. So y2 is the unrestricted. And remember, if there is unrestricted variable, we need to change from y2 into y2 accent and y2 double accent. Y2 accent minus y2 double accent. Yeah, everything changed into those. Yeah, here, put it on the constraint, and now we have quite a lot of variable now with the r as well. If we use big M, yeah, this is longer. Yeah, but by the end of the day, we get the same result. The W is 54 4 by 3 with the Y and 1, yeah. Yeah, so we still have the same optimality. Okay, so that means the dual is good. Yeah, this is maybe, yeah, you will probably will not do the dual in reality because the primal is fine. There's no problem with the primal. It's finished, yeah. But if we have another problem and you cannot find a solution in it, or too long, too difficult to find, and then if you try to make the dual and it turns out that your dual has solution like this, then you know that the z will be same, will be 54 4 by 3 for the 5. That means there is a configuration of x1 and x2. Yeah, there is a configuration of x1 and x2 and x3. Yeah. And then you do this, and then with additional analysis, you will find out the x1, x2, and x3 based on the y. Okay, so this is it. Yeah, for duality, for the intro to duality. Okay, up to this point, any question? No, it's clear, and I hope it's good. Yeah, because that's all there is. Yeah, for, for the UTS, we until these slides. Yeah, until this slide. Okay, so I'm gonna try to upload. Where is it? There's two file. Okay, there in the chat. You check the chat and you can download it. Two file. Yeah, practice. Basically using example. Assignment, I mean, for the graded assignment for this, maybe not, but for you guys to what can I say? Just try the exercise. There's several example that there's the answer, and then you can try to redo it without looking at it and see if you do it correctly or not. Whether it's just primal simplex, the big M, two-phase, or including the duality. Yeah, I think there are several examples that we can try to do it yourself. And if you find something on the internet as well, you can just use the lingo to find the result. If the result looking good and not too complex and look like it can be done manually, You can do it. Yeah. You can try to train. Yeah. If you remember the Lingo software that I give you example, when you run it, you can see how many iteration the Lingo is using. Yeah. Let me share it one more time. Okay. Okay.
Sorry, Pak.
Yeah.
May I ask about the absence in Gapura? Because
The
for
what?
me, I think I forgot to fill up one of the absence for
Oh
the
yeah,
first
I
semester
haven't make. I
application.
will make it. I will just make it, and I think
Oh,
just
okay.
everyone is
Thank you,
there.
Pak. And also, I want to ask about the. I want to ask about the like the material for the midterm, Pak. Do you have like
Yeah.
kisi2 or something?
Because we can say that usually mm, could be five, no, four, max five problem maybe. So they usually have problem related to formulating a problem into mathematical formula. Yeah. From a story, then you need to make the mathematical formula out of it, and it could be added with try to find a solution graphically or totally different number for the solution of graphical method. And then there will be question about simplex. Yeah. Now the simplex can be there is some variation. Yeah. Could be primal. Could be the one that added big M or two phase. Yeah. And you could choose, or it's instructed to use a certain method, big M or two phase. Okay. And then the simplest also can be same number or different number. We'll ask if we change this. Now that's a question of if. Yeah. What will happen? Then it's going to be sensitivity analysis that we just discussed today. And then and then there is also another one that's related to the special case of simplex, which means is this alternate solution? Is this infeasible solution? There might be also a question about that. Like example, this is the last result. What you can see? What can you conclude from this final or optimal solution? Maybe you can process one more iteration to see if it's alternate solution, or you can also already find out that is invisible, yeah, or unbounded. Which one? Maybe question about that. And lastly, it may also come up. Okay, find the dual of this primal example. Okay, so those are. I think every year is like that. The question is like that. It's just matter of what kind of problem. Yeah. So that means you need to bring. I don't know if we have it, but calculator probably is fine. If it's not, that means the number is should be easy to calculate manually. Yeah. I don't know. Have you seen if there any requirement can you can use calculator or not in the Gapura or in the announcement about the schedule of the midterm? I don't check it yet. I haven't checked it yet. Yeah. If we use calculator or not, and then if it's open or closed, do you know? Is there any announcement? Okay. So okay. It might be closed. Yeah, I need to warn you, it might be closed book, which mean that you need to understand the way to do it. Yeah. The procedure, the steps by step on how to do the simplex, for example. What's the meaning of this certain number of coefficient in the sensitivity analysis? What's the meaning of unbounded? Which number shows that this is unbounded solution? That means you need to memorize those. Yeah. if it's closed. If it's open, then of course you can print everything that you want, slide or book, yeah. Uh, but the time usually is really very limited. The time, yeah, yeah. So be mindful of that. And this is the lingo that I show you that you know if you can see that you get, oh, for this problem, lingo only use two iteration. Meaning, if you do simplex, we might just do two iteration as well. Yeah. So this is a good example for you to practice. You know the result, the final result, and then you can do the practice with only two. If it's mentioned like 20, don't do it. You it means 20 simplex iteration, 20 tables, making you dizzy. Yeah, it will not go out on a midterm. Midterm iteration maybe two, maybe three, rarely four, I think. Yeah. But definitely not five. I think. That's too long. Yeah. Okay, for the simplex.
Okay, Pak.
Okay.
Thank you so much.
Any additional question from this point?
So, but for the preparation for the midterm exam, so we just study all the PowerPoint, ya, Pak?
Yes. And if you want to practice, you can use the one that has you do you have in the PowerPoint, or if you find other example on the internet, or you just made up numbers, try the lingo and see if there is solution and how many iteration does it have. And if it's not long, two, three iteration, you can try to do the simplex. Yeah. Which this is the key answer, the solution is using the lingo. Yeah. Z and what else? Yeah, this is the X1, X2, and so on. Yeah. Okay. All right. But before this is the math. You need to also learn about how to change from a story into a mathematical model. Yeah. Again, use the one that we have. But one that I show you is for the linear one. No, there is several other. If you do internet, there is so many other that are very complex because they are not linear. But we're limiting ourselves to the linear problem. Yeah, you use the nonlinear in a PO2 or second OR and partly in the session two. Okay, all right. So yeah, sure. Kind of, because if you run and it's invisible, that means your model is not correct. This is it says invisibility zero, and you have optimal solution, which means your mathematical kind of have a solution. I don't know if it's completely correct or not, but if it's invisible, then there is something wrong with your formulation, definitely. Okay, yeah, okay. Any other question? All right, I'm gonna stop sharing and try to close the window. All right, so this is it, yeah. I know that most of the time that we do it online, not on the campus, but I hope that you can still understand and get what we discuss, yeah, to prepare you not just the exam actually. Exam is partly and only midterm, not the final exam, but for the future as well. If you happen to have to discuss about something related to OR, ya, operational research, or penelitian operasional Indonesia, then you can go back to this slide and check and see, yeah. Specifically, sensitivity analysis that may be helpful if you need to kind of compete with the other colleagues in work, for example, yeah, to get better solution or quicker solution. That. Okay. And thank you for coming to this Zoom meeting, and I hope you have a good time to study and good grade for